Picture this. You step through a shimmering doorway, a portal humming with impossible energy, and boom, you emerge in 1969. You're there, on the dusty lunar surface, watching Neil Armstrong take that iconic first human step. The sheer mind-bending awe of witnessing history unfold live right in front of your eyes. Cool, right? The kind of cool that makes you want to drop everything and figure out how to get there. But that shimmering doorway isn't just some Hollywood special effect, some glittery bit of movie magic. We're talking about a wormhole, a theoretical shortcut through the very fabric of space and time. And here's the kicker. Einstein's mind-blowing math, the equations that govern our universe, actually say these things might be possible. So, is it time to dust off your bell-bottoms and practice your moonwalk? Not so fast. There's a catch. One brutal, universe-sized obstacle that's blocking every single path to yesterday. It's like having a golden ticket to the past, but the universe keeps slamming the door in your face. But stick around, because in the next few minutes, we're going to crack open those equations, take a wild ride through a Kip Thorne-style time machine, the theoretical blueprint for time travel, and confront the single stubborn thing that's keeping the past safely off limits. Get ready, because this is where physics gets wild. Most people hear the word wormhole, and their minds immediately conjure up images of a glowing, swirling space tunnel, maybe with some trippy visual effects. You know, something straight out of a sci-fi blockbuster. But when physicists hear wormhole, they often think of something a bit more mathematical. They think Einstein-Rosen bridge. This isn't some recent speculative idea. It's a solution to Einstein's general theory of relativity, first sketched out way back in 1935 by Albert Einstein himself and his colleague Nathan Rosen. The concept is surprisingly elegant, almost deceptively simple. Imagine our universe as a flat sheet, like a stretched-out bed sheet. Now, take two black hole-shaped dents in that sheet, massive gravitational wells. The Einstein-Rosen bridge suggests you could, theoretically, glue the singularities of these two dents together. And presto, you've got an instant shortcut, a direct tunnel connecting 2 points that could be light years apart in normal space. Sounds fantastic, right? A cosmic superhighway! But here's where the dream starts to unravel faster than a cheap sweater. The problem is, this elegant bridge snaps shut quicker than you can say spaghettification. We're talking faster than light itself can cross it. Anything, and I mean anything, attempting that trip would get stretched, squeezed, and crushed into oblivion before it even had a chance to say hello to the other side. It's like the universe offers you a gleaming, brand new freeway, but the moment you tap the accelerator, the road collapses beneath your tires. Not exactly ideal for your intergalactic commute. So if that initial, unstable version of a wormhole is a no-go, how in the world do you keep its throat, that crucial tunnel, open long enough for something or someone to actually pass through? This is where physics gets really weird, really fast. You need something that actively repels gravity instead of attracting it. Every single thing we encounter in our daily lives, from an apple falling from a tree to the planets orbiting the sun, is governed by gravity's pull. Ordinary matter, the stuff that makes up you, me, and everything we see, cannot repel gravity. It only ever attracts. What you need is something truly exotic, matter with negative energy density. Yeah, you heard that right. Negative energy density. This isn't just lightweight stuff. This is stuff that, in a sense, weighs less than nothing. It's a concept that pushes the boundaries of our intuition. Think of it like this. If normal matter creates a dip in space-time, negative energy matter would create a bump, actively pushing outward. Now, does such a thing even exist? Well, quantum mechanics, that incredibly strange and wonderful realm of the super tiny, offers a tiny, tiny loophole called the Casimir effect. Imagine two uncharged, perfectly parallel metal plates placed nanometers apart in a vacuum. What happens? They actually attract each other ever so slightly. Why? Because the quantum vacuum isn't truly empty, It's teeming with virtual particles constantly popping in and out of existence. Between the plates, certain wavelengths of these virtual particles are excluded, creating a slight imbalance. This imbalance results in a tiny, almost imperceptible force that pushes the plates together and, crucially, creates a region with a net negative energy density. It's a real, measurable phenomenon. But here's the bummer. The negative energy generated by the Casimir effect is ridiculously, absurdly small. Measuring it in a lab gives you numbers so minuscule, they'd make a single grain of sand look like a cosmic behemoth. A traversable wormhole, one big enough for a spaceship or even a human, would need a mountain of this stuff. We're not talking about a grain of sand. We're talking about Jupiter mass levels of negative energy, but, negative. The sheer scale is mind-boggling. And the biggest problem? No one, not even our brightest physicists, has the faintest clue how to stockpile that much anti-weight. It seems the universe has a very strict accountant, and it fine-tunes the ledger so the total energy never dips far below zero for long. It's like trying to run up a massive debt, but the universe keeps magically paying it off before you can really get going. But hey, let's pretend for a second. Let's imagine we somehow found a supply, a cosmic stash of this impossibly weird exotic matter. What then? You'd slide it like a corset, a structural brace, around the throat of that wormhole. This negative energy would counteract the gravitational pull, pushing space-time outwards and stabilizing the tunnel. Now, with the wormhole safely propped open, you could theoretically stroll from Earth to Alpha Centauri, a star system 4.37 light-years away, in about 10 minutes, without feeling so much as a jolt. Space travelers would absolutely lose their minds over that. Imagine the delivery times for interstellar pizza. But hold on, we promised you time travel, didn't we? That's where the plot really, truly twists. And it's all thanks to another one of Einstein's brilliant insights: time dilation. Here's how you'd turn that stable wormhole into a time machine. Take one mouth of your newly stabilized wormhole and park it next to something incredibly massive, like a neutron star, where gravity is so intense it warps space-time and slows clocks down significantly. Or accelerate that wormhole mouth to near light speed, another way to slow down time relative to a stationary observer. Meanwhile, the other mouth of your wormhole stays put, chilling out in normal, low-gravity space. Now let them age differently. After, say, a decade passes for the stationary wormhole mouth, the one near the neutron star, or traveling at near light speed, will have experienced less time. Perhaps only a year or two has passed for it. When you finally bring those two mouths back together, they're still connected, but they've experienced different amounts of time. Each end now opens onto the same spatial location, let's say Earth in the year 2040. But here's the magic. The dial on the slowed-down, younger wormhole mouth reads 2030. So what do? You hop through that younger mouth and boom! You exit 10 years in the past relative to the external universe. Congratulations, my friend. You've just built a closed time-like curve, or CTC. That's physicist speak for a cosmic subway loop that visits yesterday. It's the theoretical holy grail of time travel. This isn't just some wild speculation. In the late 1980s, the legendary physicist Kip Thorne and his students actually ran the numbers on this exact setup. And guess what? Their calculations showed that, according to the equations of general relativity, this bizarre time-traveling wormhole configuration could exist. It was mathematically consistent. But, as always, there's a catch. And it's a big one. The quantum vacuum, that empty space teeming with virtual particles, doesn't stay quiet when you start messing with time. Fluctuations of light and matter, those tiny quantum jitters, would start to pile up on themselves near the wormhole mouth. They'd spin around the time loop, amplifying like sound feedback in a stadium when a microphone gets too close to a speaker. This amplification would skyrocket, causing the energy density to blue shift to infinity. In layman's terms, the energy would become so incredibly immense and concentrated that the wormhole would self-destruct in a violent burst of gravitons, the theoretical particles that mediate gravity. Stephen Hawking, the brilliant mind who gave us so much insight into black holes, famously called this the chronology protection conjecture. It's his idea that the universe itself steps in and tears up your time travel ticket before paradoxes can even happen. It's like an invisible cosmic bouncer, preventing anyone from messing with the timeline. In short, nature seems to have a deep-seated dislike for time tourists. It's almost as if the universe has its own set of unbreakable rules, and causality is at the very top of that list. No going back to kill your grandfather, no matter how tempting it might be for some movie villains. But don't think for a second that scientists have just thrown in the towel. Recent work, fueled by an insatiable curiosity, hasn't surrendered to Hawking's conjecture. A fascinating paper from 2023, for instance, explored the idea of ring wormholes. Imagine a donut of negative energy, not just a spherical shell. The authors claimed that the curvature of space-time could be tuned in such a way that the quantum feedback, while still present, might become finite, not infinite. That means the wormhole might not immediately self-destruct. Even then, the authors were quick to admit that this ring wormhole would still need contributions of negative energy from sources we can't even begin to harness. We're talking Casimir-like effects, but perhaps from extra dimensions, or even generated by quantum entanglement on a massive scale. Neither of those is something we can engineer with today's technology, or even tomorrow's for that matter. Speaking of quantum entanglement, there's another mind-bending idea championed by physicists like Juan Maldacena called the ER equals EPR conjecture. This speculates that every pair of entangled particles, those quantum buddies that instantly affect each other no matter the distance, is secretly connected by a quantum wormhole. It's a wild thought, right? It sounds like a cosmic subway map, where every entangled particle pair is a tiny hidden shortcut. But translating this micro-entanglement into a macroscopic traversable time machine for humans? That would require vast numbers of qubits, the building blocks of quantum computers, maintained in coherent states far beyond anything our current technology can even dream of. We're talking about engineering on a scale that makes building the pyramids look like stacking Legos. The upshot of all this cutting-edge research? The equations still allow for time travel, but the engineering slope is Everest steep, and we're still stuck at base camp. Okay, so building one seems like a colossal headache. What about finding one? Could we discover a naturally occurring, traversable wormhole out there in the cosmos, instead of having to build one from scratch? Astrophysicists have certainly been on the hunt for signatures. They're looking for telltale signs, sudden extreme lensing events that warp the light from distant stars in a unique way, or repeated light curves from a single source that suggest light is taking a shortcut. They're even searching for gravitational wave bursts with a distinctive echo that might indicate a wormhole forming or collapsing. But so far, the night sky remains stubbornly, frustratingly silent on this front. Without that exotic matter floating around in interstellar clouds, any primordial bridge that might have formed in the early universe would have imploded within microseconds of its creation. And those incredible black hole mergers detected by LIGO, the Laser Interferometer Gravitational Wave Observatory? The data perfectly matches the vanilla general relativity templates for colliding black holes. No after-wormhole whispers, no strange echoes, nothing that suggests a cosmic shortcut was involved. It's a clean, straightforward collision, just as Einstein predicted. And what about those pesky paradoxes? The grandfather paradox, where you go back in time and accidentally prevent your own birth. Some clever theorists argue that attempting to change the past wouldn't actually alter your past. Instead, it would simply shunt you into a different Everett branch, a parallel universe where your actions play out. This interpretation, tied to the many worlds interpretation of quantum mechanics, would neatly dodge the grandfather paradox. But here's the catch. It also means you'd never return to your original timeline. It's less a round-trip ticket to history and more a one-way exile to an alternate reality. Neat for fiction, absolutely useless for historians who just want to film the Library of Alexandria before it burned down. You'd end up in a different universe's Alexandria, maybe one that never burned, but you couldn't bring the footage back to your own. So let's tally the score, shall we? Einstein's equations? Check. They definitely allow for wormholes and even time travel, theoretically. Exotic matter? Maybe in thimblefuls, thanks to the Casimir effect, but we need Jupiter-sized mountains of the stuff. So, a big fat question mark there. Stability? Shaky at best, and probably only achievable with that impossible exotic matter. Quantum back reaction? Probably fatal, thanks to Hawking's chronology protection conjecture. The universe seems to have a built-in no-time travel policy. Observational evidence? A resounding 0. The cosmos isn't giving us any hints. Put all those together, and the dream of stepping into yesterday remains exactly that, a dream. A beautiful, tantalizing dream painted in chalk on the blackboard of theoretical physics, but a dream nonetheless. So, the next time a movie hero dives through a swirling CGI portal to stop a villain in 1930s Berlin, enjoy the popcorn? Absolutely. But remember the fine print. Without mountains of negative energy, and a universe suddenly willing to look the other way on causality, that portal slams shut faster than you can say grandfather paradox. It's a great story, but not exactly a travel guide. Are physicists giving up? Absolutely not. Every new quantum gravity model, every new calculation, inches us closer to understanding whether chronology protection is an absolute, unbreakable law of the cosmos, or just really, really good at hiding loopholes. Until then, the past stays safely, stubbornly out of reach. It's a tantalizing mystery, one that keeps us dreaming and keeps us pushing the boundaries of what we think is possible. If you learned something wild today, if your mind was just a little bit blown by the sheer weirdness of our universe, then you know what to do. Tap that like button. It tells the algorithm that we're allowed to bend time and space with our brains every now and then. And if you're curious about how the Casimir effect actually measures negative energy, or want to dive deeper into the mind-bending world of quantum mechanics, then watch our other quantum mechanics videos on time pilgrimage, and don't forget to subscribe for more physics that walks the razor-thin line between possible and impossible.